Hello again, it's your friendly heavy physics teacher, and this is my online lesson for my college physics class that covers Unit 9, Lesson 3 on electromagnetic induction. Um, Today we're going to specifically devote our time to talking about the principles behind how an electric motor works. Okay, we're not going to get right to electric motors today, but we're going to get to the principle on which an electric motor system is based. Okay, so here we go. Now, we're going to use the third right-hand rule for this. And the third right-hand rule is this. The induction of a mechanical force caused by the magnetism, the induction of a mechanical force on a conductor, usually a wire, when current flows through the conductor. That's what this is dealing with, the third right-hand rule. Okay? It is an aspect of electromagnetic induction. Okay, so you see the equation here that's on your reference table, FB equals ILB sine theta. This is the equation that will give you the magnitude of the force acting on the wire. All right? What in heaven's name are you talking about, Mr. Welkley? Good gravy. All right? Give me a moment here. All righty. Imagine, if you will, that these are two poles of a U-shaped magnet. Imagine the magnet going down below the table here, looping a little bit, making a U, and coming up. So this would be the one end of the magnet. This would be the North Pole, and this is the South Pole, okay? And we have this wire that's running in between the two poles. If I were to cause a current to flow through that wire, what do you think might happen? Okay, well, we know this. As the current flows through the wire, it's going to produce what around the wire? From the previous lesson, it's going to produce its own magnetic field. Aha! So we know that, let's say that the current is flowing toward me through the wire. All right, so using my first right-hand rule, put my thumb in the direction of the current. Yes, that means you can't see it. Let's reverse the flow. Current's flowing this way. Thumb goes in the direction of the current, and my fingers wrap around the wire. Okay, so that means, according to you, there is a clockwise rotation to the magnetic field, or a clockwise direction to the magnetic field. Okay, I hope I'm getting that right, because for me it's clockwise. For you it'd be counterclockwise. Okay, now the magnetic field, the part of the magnetic field around this wire that's going up and down on the sides of the wire, don't do anything to the magnetic fields here. But the part of the magnetic field that's coming up, all right, is now acting parallel to the magnetic field caused by these two poles of this magnet. So we're going from the N pole to the S pole. So the magnetic field of these two magnets is going from over here to over there. Okay, from your point of view, that would be from your left to your right, I think. All right, I'm still getting used to how the camera stuff here works. But regardless, the direction of the B field is this way. But the direction of the magnetic field, the B field of the wire on top, is going this way. And what do opposite fields tend to do? Attract. Okay? The ones on the bottom are going this way. So underneath this wire, current going toward you, underneath this wire, they're going that way. Oh, wait a minute. That's the direction of the magnetic field. When you have two magnetic fields that are acting in the same direction, that means that they're going to repel. The effect is that if I were to cause a current to flow through this wire right here, right now, and these were magnets, we would see the wire do this. All right. It would literally, quite literally, pop up. It'd be forced to move up out of the field and it would accelerate upward. Okay. So that's the mechanical force I was talking about. This is creating true mechanical motion of this wire upwards. The amount of that force depends on how strong the field of the external magnet is, how much current is flowing through the wire, and the physical distance of the wire that is exposed to the magnetic field here. Okay, so F, the magnetic force acting on the wire to move it, is equal to the current flowing through the wire, I, the length of the wire exposed to the field, times the intensity of the magnetic field that's interacting with the wire, times the angle that is between the direction of the current and the direction of the magnetic field. Notice that when they are perpendicular, sine of 90 degrees is 1. So I get a maximum force when I have a perpendicular relationship here. Notice that if we turn this wire like this, if these were separated more widely, and we had the current flowing, doesn't matter which way, left or right, notice that the angle between the B from the North Pole to the South Pole and the angle for the current is either 0 or 180. Sine of 0 is 0. Sine of 180 is 0. So there would be no force acting on a wire moving this way or oriented this way in the magnetic field. Okay, do we see that? Pretty cool, huh? All right. That's the principle on which the electric motor is based. We'll get to why that is in a little bit. Okay, I need to show you how to use the third right-hand rule with diagrams that are on two-dimensional surfaces, i.e. a page of paper or the whiteboard that I'm going to use. Okay, so one moment. Okay, if you would, sorry for the click there. Decided to change how I wanted to do this. If you would, make sure you get, if you haven't already downloaded it, download it, print it, get it on the table in front of you, get it on the desk in front of you, get it wherever you want to use. All right, so get it right now. I'm going to pause here. You pause there. I hope you paused, okay, because I did, and that's why we got the little interaction there. Okay, third right-hand rule is all about the FBI rule, all right? In other words, F equals ILB, or I like to switch it around just a little bit, use the commutative property of multiplication. F equals BIL, or F equals BI, or the FBI rule, because the FBI investigates crimes. We're using FBI to investigate how magnetism mysteriously affects electric current. All right, so the FBI rule. Here we go. Right hand rule. All right, make sure you orient your hand this way. Okay, your fingers are going to represent the magnetic field lines or flux lines, as Michael Faraday called them. All right, so the magnetic field lines, there's lots of them in a given space, so that's why all of our fingers represent the B field. Your thumb is going to represent the current that's going to flow in a wire. It's also going to represent the direction of motion of positive charge. Okay, so keep that in mind. Conventional current. Your palm is the force acting on the wire. Think about it this way. If I were to push on a grocery cart, would I push with the back of my hand? Would I push with the tips of my fingers? No, I push with my palm. So I exert a force by doing that with my hand. Imagine this in 3D. Whoa. Okay? All right? So, F is coming out of my palm. B is my fingers. I is the current in the wire. F, B, I. Notice I have a three-dimensional plane here, a three-dimensional coordinate system. Force, magnetic field, current. Notice if I put my thumb like this, what's the angle between my thumb and my fingers? 0 degrees. What's the amount of force when the angle between B and I is 0? Well, sine theta, theta is 0, sine theta of 0 degrees is 0. No force. So even though visually my hand could exert a force, until my thumb is out here, electrically, electromagnetically, it doesn't do anything. Okay? So, I'm going to show you some diagrams. We're going to use our third right-hand rule to figure out which way the force is going to be acting on the wire. Okay? Okay, we have two different diagrams here. And just ignore the right side for right now. Ignore this side over here, whatever orientation. That, I guess that's the left side for you. Look at this side first. Okay? So, here is the pole of a magnet. Here is the opposite pole of a magnet. Could be two different magnets. It could be a U magnet where this goes down, around, out of the page and comes back up on this side. Suffice to say, I've got two opposite poles of a magnet creating a magnetic field that's interacting with the wire. Okay? Let's imagine that the current is flowing down through the wire. So positive here, negative here. The conventional current is flowing down through that wire. All right? If that's the case, let's make it go up because my handle. No, let's make it go down. Okay, so that you can see this. All right? So, what is the direction of the magnetic field for this diagram? The direction is from north to south. That's our definition of magnetic field. The current is down. Notice which way would my palm push the wire if it were behind the wire? Notice it would push it out towards you. Okay? So what I would do is I would write on this, if the current were flowing up, if this is the direction of my current, then I would say this is the direction of the force acting on the wire. Do you see that? Okay. Notice that if you flip the direction of the current in the wire, if the current's going down, the force also flips. The force, instead of coming out of the page, is going into the page. See how that my palm would be pressing down on the wire if that were the case? And that's all because the magnetic field, the external magnetic field created by these external magnets, is interacting with the part of the magnetic field that's around this wire to create attraction and repulsion that results in a net force either acting upward or downward with this orientation of the wire to that magnetic field. Okay? Over here with this one, let's say that instead of knowing the current, we knew that this was the direction of the force acting on the wire. And we call it FB because it's the magnetic force. It's the force caused by this magnetic field acting on the wire. All right? So, again, north to south. That's the direction of my bead field. So my fingers point that way. Notice that my palm has to act up. So the current, the natural direction that my thumb is going to point based upon all of that is out towards you. And so I would designate that as I, that way. Okay? All right. Another type of diagram that you will see for the for problems involving this. Okay? This time, instead of the magnetic field going sideways, we have a magnetic field that's either going into the page or coming out of the page. Okay? Let's say for this one, we know that the current is going that way in the wire. Okay? If the current is going that way in the wire, which way will the force act on the wire? Okay, so magnetic field B, my fingers, flux lines, going into the page. Current is going that way, so that's why my hand is this way. Notice which way is my palm oriented? It's oriented toward the top of the page. It's oriented up. So that's the direction that the force would be acting on the wire. So I would write that as that way. Okay? Over here, let's say that the current is, or no, let's say that we know that the force is acting that way on the wire. Okay? So the force is acting to the right. So that would mean I need to point my palm to the right. The thing is, my palm points out of the board. Okay? Do you see how I'm doing that? Or my palm points this way because that's the direction of the force acting on the wire. My fingers have to be pointing out of the board, okay, out of the page. And so notice that my thumb, which way does my thumb point? Up. Notice if I reverse either the force or the magnetic field, that causes my hand to go the other way and my thumb goes down, okay? So for this orientation of the force, the magnetic field coming up out of the page, the current here is going up. That would be the direction for I in this. Okay? Now, a flow of current means that electrical charges are moving through space. The space happens to be a conductor. Okay? The space happens to be a conductor. Aha! That means that in the wire, in the length of the wire, if you determine the time it takes for the charge to flow through the wire, you can determine its speed down the wire. What if you don't have a wire? What if instead we have free charged particles flying through space? Cathode ray, that's stream of electrons. We can also do a stream of protons. That's what they do at the Large Hadron Collider. It's a flow of charged particles. Any stream of charged particles will have its own magnetic field and therefore will interact with an external magnetic field in the same way we were just describing. So, force on a stream of charged particles. For instance, a cathode ray, which is a stream of electrons. We can do the math. I'm not going to do it for right now for you, but we could do the math and show that the same equation we just used, F equals ILB sine theta, transforms into this equation, F equals Q V B sine theta. FV is the magnetic force causing the particles to change their direction. Q is the charge of the particles that are moving. Okay? You use the charge of each individual particle, not the whole stream. You don't worry about the whole stream. You worry about individual particles within the stream. Okay? V is the speed the particles are moving in the magnetic field. B is the magnetic field intensity. Theta is the angle between the direction of V and the direction of the magnetic field. Okay? So how would this work in a diagram? Let's say we're at the Large Hadron Collider, and we're going to take a stream of protons and fire it through a magnetic field, all right? And if we fire the protons perpendicular to the direction of the magnetic field, something's going to happen to them. Okay, so what is the charge of a proton? Oh, yeah, charge. It's the elementary charge. What is the sign of the charge of a proton? Positive. Okay, so I can use my conventional current rules when I'm talking about a stream of protons. If I were to use electrons, if I were to use negative ions, then I would have to remember that I is in the direction of flow of positive charge. They're actually moving opposite in that direction. Okay, so here we go. This is essentially I for this example. It's the motion of the particles into the field. So that's my thumb. Okay, magnetic field lines, the flux lines. Okay, those are the X's. The magnetic field is directed into the board. All right. Notice that if I put my hand, fingers in the direction of the magnetic field, thumb in the direction of the motion of positive charge, I have to say motion of positive charge. Notice that this, right at the instant the particles enter the field, the force is acting perpendicular to it. But the particles are no longer confined to the confines of a wire. They can move freely in space. So a force that acts perpendicular to their motion, what does it do? If you were running forward and someone pulled on your belt sideways, what would you begin doing? You would begin turning, correct? That means at the next instant of time, that's the direction of motion. But now look at which way the force would be acting. All right, I go from being straight up to being at an angle. Now they're moving this way. Again, move the force acts, in other words, the force is acting continuously perpendicular to the motion of the particles, and it would create a situation where this would be the motion of the protons moving in the field here. All right, notice that no matter where you are, the force is acting perpendicular. If you have a strong enough field, you can actually cause these to spin around. Okay, you could create a circle and it would perpetually go around in a circle once they entered the field. That's the reason that the Large Hadron Collider is shaped the way it is. Okay, so there we have it, the principles behind how an electric motor works. The next video lesson is going to be entirely on how we translate what we just talked about today into electric motors, okay, and how we can scale up an electric motor to be able to do the amazing things that we do with electric motors today. Okay, thank you very much for watching. Once again, this is your friendly heavy physics teacher signing off for this lesson for my kids at Tamarack High School. Have a good one.